So we've already talked about voltaic cell electrolysis, which in the scheme of this chapter I find to be a lot more important. But most books also focus on metal electrolysis, i.e., where we get our pure metals from, right? They have to dig up these metals from the earth. How do we turn them into pure metals? Well, we apply a voltage. And it's a complicated process. It involves complicated calculations, complicated indications of purity, and a lot of cross reductions with a number of other metals. So I try to talk about that a little bit and some of the issues that we deal with in real life, but for the exam I'm mostly going to focus on voltaic cell electrolysis. So when it comes to metal electrolysis or electroplating, what we're going to do is create a brine. Now in some cases you can digest some kind of metal ore in some kind of acid bath is really common. Another approach you can is just to heat up, in this case aluminum oxide, to a high enough temperature that the ions separate, either in a bath, it could be an acidic bath, or it may just be heated up that this whole salt just turns into liquid. Now we're talking extremely high temperatures either way. But then what we're going to do is apply a voltage here. And by applying a voltage, now the electrons need somewhere to go. They are going to be attracted to the positive 3 aluminum. The oxygen is now going to be attracted to the positive anode. And so both of these elements will be changed back into their elemental form. And you're going to be able to plate pure aluminum on the side and then sell that aluminum to an aluminum manufacturing company of some kind. So this is what they have to do for pretty much all metal ores, and it's a pretty involved concept. Now, one of the things the book wants you to do is to make calculations based on the energy of this transition process, how much energy is needed to plate like 500 grams of aluminum. I don't really care about that, I just want to introduce the concept. If you go into something like electroplating, then you can worry about these calculations. It's not too important to most chemists. So this is a simple application of this that I don't usually use in tests because this book doesn't have any problems that look like this. But let's say we dig up some lead bromide ore and we want to sell off this lead ion for whatever reason. Well, you can either heat or acidify this metal ore until it splits in ions. Now, we are going to use lead in the cathode, so we get lead metal. Again, this is a non-spontaneous half cell. We are also going to have to either provide or from the ore itself have an anode that exists where we can apply voltage to create products, and that's even a higher voltage. So we are going to end up with a negative voltage, which means we need to apply 1.49 volts to this process. And again, because we started with lead and bromide ions, we're going to get out lead metal and bromine gas. This problem gets even uglier if you're trying to plate metal with impurities. In this case, we want to electroplate iron to make pure iron metal. Unfortunately, we have lead in this process. And as you can look at these half cells, it's actually easier to electroplate lead, right? It's less negative. And so the lead is going to plate first. And so no matter how much energy you add into the system, the easiest half cell is always going to go forward. So we're actually going to have to electroplate out lead until all the lead is gone, and then electroplate out the iron. And so that's a real issue that people have to deal with when they try and electroplate metal out of impurities in ore. This is a good example of where this gets even messier in real life, because not only do we have this copper reduction that we want to get, but the total voltage of this is also going to be determined by the water solution. In this case, if we have a basic solution in copper sulfate, the sulfate doesn't react, but we can actually use the anode to run the formation of water from hydroxide. So in order for this voltage to work, we have to be in basic media. If you're in neutral media, there's not enough hydroxide to go around to make this reaction run. And we can start to plate copper on this cathode. Again, this is a real problem though. If it's acidic, this voltage is going to be different. If it's neutral, this voltage is going to be different. And so you've got to experiment, right, with what impurities are there, what medium is going to work best to get rid of these impurities, and finally, what medium is going to work best to electroplate your metal. And for that reason, I'm not too worried about these problems. I want you to get the idea. I think it's kind of neat. The actual calculations for us are not super important.